Another notation of complex numbers is the exponential form. This form solves powers and roots much shorter than de Moivre's solution. Welcome to Mathematics of Engineering. Referring back to the polar form where z is equal to cosine of theta plus I times sine of theta, the terms inside the bracket is then reduced to e raised to I times theta through integration. This is known as the Euler's formula or Euler's identity. Thus, the complex number can be written as r times e raised to I times theta, where theta is in radians. Let's now review all the notations of complex numbers. First is the Cartesian or rectangular form, which is presented as z as equal to a plus or minus b times I. The second notation is the polar form, which is z as equal to r cis theta. This is expanded as r times cosine of theta plus I sine of theta. Then the third notation is the exponential form, which is through z as r times e raised to I times theta. For the first form, the important parameters are the real and imaginary coefficients, a and b. The polar form works with the modulus r and the argument theta. This is also true for the exponential form. Say we are to transform the coordinate pair 8 pi over 2 into its Cartesian, polar, and exponential forms. The first term 8 in the coordinate pair is r, and the second term half of pi is theta. These are the necessary parameters to complete the polar and exponential forms. So to transform these into polar form, we write z as the modulus 8 times cosine of pi over 2 plus I times sine of half of pi. In exponential form, we still use r and theta in the equation, making it z as 8 times e raised to I times half of pi. For the Cartesian form, we simplify the polar form by multiplying 8 times cosine of pi over 2 to take the real number 0. 8 times sine of pi over 2 times I gives 8 multiplied by I. The next coordinate pair has 4 and a third of pi, still to be transformed into the Cartesian, polar, and exponential forms. Take a look at the coordinate pair. 4 is the modulus r, and pi over 3 is the argument theta. These are plugged into the polar format to have z as 4 times cosine of pi over 3 plus I sine of pi over 3. We also do the same for the exponential form, mainly just plugging r and theta into the format, which makes z as 4 times e raised to I times pi over 3. Again, in Cartesian form, we use the polar format and simplify the terms, so take 4 times cosine of pi over 3 to have 2. And 4 times sine of pi over 3 is 2 root of 3 times I. The next coordinate pair has 6 and 75 degrees. Just the same, 6 is the modulus, and 75 degrees is the argument. So in polar form, take z as 6 times cosine of 75 degrees plus I sine of 75 degrees. Also in exponential form, theta should be in radians, so convert 75 degrees into radians by multiplying the conversion factor of 2 pi is to 360 degrees, and get 5 pi over 12 radians. Then the exponential form is taken as 6 times e raised to I times 5 pi over 12. In Cartesian form, we use the polar form of z, then multiply 6 cosine of 75 degrees and get 3 root of 6 minus 3 root of 2 all upon 2. Then 6 sine of 75 degrees come up as 3 root of 6 plus 3 root of 2 upon 2 times I. We can leave the terms as is or take their decimal counterparts as z equal to 1.5529 plus 5.7956I. Another type of transformation is from exponential to Cartesian formats. Say we are to convert 4e raised to I times pi over 2 into its Cartesian form. We identify the r as 4 and theta as pi over 2. In polar form, we have z as 4 times cosine of pi over 2 plus I sine of pi halves. This is used to take the Cartesian form, so multiply 4 by cosine pi over 2 to get 0 for the real number. Then 4 times I sine of pi over 2 to have 4i for the imaginary. So z is 4i. The next example is to transform e raised to I times pi over 4 into its Cartesian form. The modulus in the expression is 1, and the argument is pi over 4. Having both r and theta, the polar form becomes 1 times cosine of pi over 4 plus I sine of pi over 4. In Cartesian form, multiply the terms in the polar configuration. So 1 times cosine of pi over 4 is root of 2 over 2. By multiplying 1 times I sine of a quarter of pi, we get root of 2 over 2i. How about converting e raised to negative I into its Cartesian form? Note that the modulus is 1, and the argument is negative 1. Place these values into the polar form to have z as 1 times cosine of negative 1 plus I sine of negative 1. For the Cartesian form, multiply 1 times cosine of negative 1 to have 0.5403. Then 1 times I sine of negative 1 is negative 0.8415i. The third transformation type is to convert a Cartesian form into an exponential form. If z is 1 plus I, we convert this into its exponential form. The complex number in this form contains 1 as a and negative 1 as b. Before solving for any transformation, take time identifying how the complex number looks like. Graph it with positive real and negative imaginary numbers, and see that the vector is in the fourth quadrant. Now solve for the modulus r by using the root of a squared plus b squared. That will be the root of 1 squared plus negative 1 squared. That gives r as root of 2. Theta is solved as the inverse tangent of b over a. So we get the inverse tangent of negative 1 over 1, turning out as negative 45 degrees. This is like rotating clockwise from the horizontal axis, which coincides with the original vector. So we can use negative 45 degrees or 315 degrees if you prefer to have a positive theta. Take note that theta should be in radians, so have this converted to radians, and that is 7 pi over 4. From the exponential format, we plug r and theta and get root of 2 times e raised to I times 7 pi over 4. How about taking the exponential form of negative 2 minus 6i? With the form, we see that negative 2 is a and negative 6 is b. Graph the complex number with -2 on the x-axis and -6 on the y-axis, so the vector is in the third quadrant. Now solve for r using Pythagorean theorem. That is the root of -2 squared plus -6 squared to get to root of 10. Theta uses the inverse tangent of b over a, which is the inverse tangent of -6 over -2 to get 71.565 degrees. You can also place your calculator in its radians mode to directly have the argument in radians. For our discussion, the arguments taken in degrees to clearly and easily illustrate where the vector is, as most students are more familiar with degrees. Take note that 71.565 degrees lies in the first quadrant. This is also the opposite vector from what we are solving, so make the argument coincide with the vector, add half a revolution or 180 degrees to have 251.565 degrees. This is converted into 4.3906 radians. Therefore, z in its exponential form is 2 root of 10 times e raised to I times 4.3906.